Well, hello. So, section 9.1 is a little introductory piece into the three-dimensional realm, if you will. Um, Talking about the X, Y, Z plane. Sometimes you'll see it written kind of like this. You go X, you go Y, you go Z. That is great. If I'm in the room and you ask me where's X, Y, and Z, X and Y are on the floor and Z is up, that's how I will draw it always. If I'm drawing on the chalkboard, I'm drawing on this is my chalkboard, and then X is this way, Y is this way, and Z is out of the board. That's just how I will kind of draw it, because that's the way it makes sense to me. The reason I make a big deal about, the reason I don't make a giant deal about this, I should say, is because over the years, what it really boils down to is understanding that wherever you decide to put the X and Y axis is where you decide to put it. You don't wander around the room. Oh crap! I smashed my head on the X, Y. I hit the origin. Someone left a dadgum origin in the middle of the room. I tripped over it or something. I mean, it's weird. The origin is wherever you want it to be, and the axes can be wherever you want it to be. Here's a swimming pool and a high dive, and it's not quite to scale, but anyways, the normal human being goes, all right, there she is. She's going to pitch herself off of this thing into this little pool down here. Isn't that great? The normal person puts 0, I think, at the top at the pool level. That's what I think a normal person does, and I believe this is the y-axis going up and down. That's the way I would do it, but you do you, friend. You are more than welcome to put the origin here at the bottom of her feet, so that it's all negative. You can put the origin at the bottom of the pool if you'd like. It's whatever. If you're weird, you put it there. It makes no difference to me. You want to call this the x-axis, and then the y-axis goes this way. You're more than welcome to do that. It wouldn't make any blessed difference in terms of how the mathematics works. She's still going to fall at the acceleration of 9.8 meters per second on her way to the ground, provided she's not carrying a parachute or, I don't know, has a trench coat that's like creating a ridiculous amount of drag on her way down, or some such like that. If she's just going to step off and give it the old pencil dive, very little resistance, and so the 9.8 meters per second squared acceleration is a fairly good approximation for reality. But again, where you put the origin, which direction you have it going. Heck, you could have the y-axis going out yonder if you wanted to, and the x going this way. That's weird, and I would judge you if you did that. I mean, I'd judge the crap out of you if you did that, but I'd mock you so hard. But she would still hit the water in however many seconds it would take to hit the water. I mean, it is not changing anything. Okay, so the reason I don't make this giant scene about it back when I was a kid, they're like, okay, take your thumb and make it go this way. That's your thumb. And then your one finger goes up like so, and you're like, all right. And then the next one points out toward Knoyers there, and you're like, wait, that's three-dimensional? Yeah, it's supposed to be. I don't know, I can do it with my hand, but I can't really do it. I don't know, I'm terrible. So I don't care, okay? I understand. I want you to understand that X, Y, and Z are all what we call orthogonal to each other. That is what perpendicular means in more than two dimensions. Perpendicular in more than 2D. Okay, anytime you're greater than 2D, we don't really say perpendicular, we say orthogonal. Okay, we talked about this back in physics. You might recall that when something falls off the table, for instance, you want to simulate a fast-moving projectile fired from a thing that goes bang, bang, and that sort of thing. You could do that. Or you could just push the stapler off the edge of the table. Here's my swing line stapler there. Yeah, all right. Give it the old push-a-rooney straight off the edge of the table. When will it hit the ground? Well, the same time one that was dropped from right here would hit the ground. It would take the same amount of time. The difference, of course, is it would do one of these numbers. Bloop. Clearly parabolic. But the time would be the same in the y-axis. And why is that? Because x and y are independent of one another because they are perpendicular, or in this case, orthogonal. That'll also be true in 3 dimensions. Now, just as an FYI, just as an aside, we'll be looking at that later on. And that independence business, okay, will also have a place in statistics. So when you're setting up a test and you want to have a couple of different X factors. So, for instance, weight and I don't know, bad breath or something, and how that will affect how many I don't know how many Pokemons you catch or something, right, on your little digital Pokemon game. Probably neither one of those have any impact on it, but I could be wrong. But I don't think that your breath has anything to do with how chubby you are or not. Okay. However, if you were overweight, there might be some things like diabetes that are not independent. Okay, and those, if you had both of those, sometimes they tend to go hand in hand. And the idea is that when you're setting up a statistical test, you want both of your x values, or all of your x values, to be independent of one another. And what you'd like them to be, or what you assume them to be, otherwise you wouldn't be doing it, you're assuming that they each have some sort of relationship or a dependent relationship on y. But you don't want the x values to have any relationship with each other. That'd be weird. Okay? And so just be aware, we'll talk more about that when we get there later on, but that idea of independence, when you're talking about that, has to do with the idea of orthogonal. And so that's something we'll talk much more about later on. We've talked about ordered pairs before, and this is, as I say, this is kind of a hodgepodge of section 9.1 and 9.2 a little bit. But in ordered pairs in x, y land, we just went 2, 5. And then in three-dimensional realms, you're going to see x, y, and z. Now, I can't say I'm going to do 9.1 and 2, but there may be some bleed over into 9.2 a little bit, okay? So don't get carried away here. 3, 1, 5. This just says you can go 3 in the x direction, 1 in the y direction, and 5 in the z direction. You're like, oh, that's awesome, Jay. Thanks, man. Appreciate that. How far is this fella from the origin? Well, I don't know. 1, 2, 3, 4, 5. Yes, you do. And what would you do to find that? Well, Uncle Pythagoras' theorem, yes, also known as the distance formula. And it's the squirt of course, 2 squared plus 5 square rooted, which is the squirt of 29. Really, it's just Pythagorean theorem. But what it really is, and I think a lot of people forget about this, is the fact if you were to draw a circle around here, square root of 29 is the radius of that circle. Or another way of saying that is that x squared plus y squared is r squared. That is literally the definition of a circle. What the heck does that say? A circle. And really, it's Pythagorean theorem. And really, it's the distance formula. It's all the same thing. You're right. Now, note, this is only the positive half of that circle. So obviously, if you were to solve this, and you're going to try to graph this, then obviously you'd have to graph it in 2 pieces, and we'll look at that in a minute. Now, it's been a while, and you're like, oh, I don't remember how to do that, Jay. Show me. Desmos is one of my favorite apps. Desmos.com. There it is. Give it to me. Love this little thing. It's the coolest. A little sad sometimes I don't get to teach math anymore at the high school level because it was fun to break this out. I still break it out with you guys and stuff, but it's just not the same, I feel like. Look at that. Look at that, will you? What do you got? Well, you got a circle with a radius of 2. That's right. Mr. Grimm, what if you did this? Boom. Oh, and it's everywhere inside of that guy, right? And so, of course, the difference being is whether we're including the circle or we're not including the circle. Boom, there you go. This is just the edge. Yeah, that's great. Now, why do I care about that? We're in 3 dimensions now. I'm glad you asked. This is 3 over on the x, 1 on the y, 5 on the z. The distance formula for that would simply be 3 square plus 1 square plus 5 square. It's 26, and 9 is 35, I think. Square root of 35. In reality, what this is doing is x squared plus y squared plus z squared equals r squared. And in reality, what is this? This is the definition of a sphere. Okay. Whenever someone gets lost, they put out a we're gonna go out in a 10-mile radius and search for them. All right. If you're a fan of the movie The Fugitive back in the day, I want to search of every doghouse, hen house, cat house, whatever, outhouse, whatever, of all these different places, right, within a 10-mile radius or whatever it was. Okay. And so clearly that's as far as they thought Harrison Ford could move, but they did not realize who they were dealing with. Okay. But anyway, Same idea. The difference here is that they would have to get off the ground and also actually underground as well to catch them if they were talking about a sphere. Okay. So kind of cool. You're like, well, could you graph that? You know, I can. So it turns out that there's a thing called CalcPlot 3D. It's pretty sweet. It's pretty sweet. We'll be using it a lot. Mostly because I have a really hard time graphing without doing something like this guy. So if you go to implicit surface, you can delete this, and you can just go x squared plus y squared. What in the same? Oh, maybe if you actually use your, I'm going to use the old, the old keyboard, I think, because I think the old writing is no bueno for me. All right, so let's do x squared plus y squared plus z squared. Nice. Equals, I don't know, let's just say 8 or something. Sweet. Boom. Oh. Okay, dummy. Okay, dummy. Yeah, maybe you go 4, dummy. There you go. I bet it works. So what happened there, obviously it got cut off a little bit because this thing's only going out to 2 maximum. To change that, if you click on this little fellow here, that one right there, you can actually change it. Be aware that, yeah, you change these guys. Here's your negatives and your mins and maxes. But you also have to change the Z clip. Kind of a noise here. So you can do this. You can do this. Go to -4 and 4. -4 and 4. And I just want to show you what's going to happen. Oh, fart. Don't do that, you idiot. Do 5. Had a bad. Well, what I want to show you is what's going to happen if you don't know this. And it's kind of very annoying. If you do this, and then you change this bugger here to 16. You're like, I can't see it, Jay. Well, what's happened here is this. Well, first of all, 2 things happened. I didn't hit enter up here. Okay, but it still's not showing. And the reason it's not showing is because the Z clips have had a problem here. And so, to fix that, you need to actually change these. And okay, that's part of our issue here. Why is this not graphing? Square root of 16 is 4. What is your freaking problem? Oh, that's the thing. You have to change it right here too. Duh. Yeah, so it's been a couple years. Oh, not been a couple years. It's been since last year, and I taught this class. I don't get to teach it anymore, so sometimes I have to kind of refresh myself. Again, if you do this correctly, you will not have a problem with it. I guess what I was trying to show is the fact that these guys here are clipped at negative. They're clipped at 4 and 4 all the time. And so if you don't change that, sometimes it'll just chop the top of your thing off. Let me demonstrate that for you. Suppose I had clipped it at 3, -3, and I didn't catch that. When you do this, sometimes it'll chop the top of the ball off, is I guess what I was trying to show. Guys, so just be aware of that. Don't freak out if that happens to you. It's okay. It's not the end of the world. Just be aware of that. You can also click on this box and move it around so you can get a peek at it, which is pretty slick. If you have your 3D glasses on, you turn them on, you can actually see it in 3D. It sounds cooler than it is. It's actually kind of dumb. But whatever. Okay, and then, of course, you can clear the plots. You can do a bunch of different things. You can add different ones. Now, some people will go like, Jay, can I graph this as a Z equals function? You can. You just gotta know what you're doing. So if you're gonna do it, you're gonna go equals the square root of parentheses. If I'm gonna do this, I'm gonna go 16 minus x squared minus y squared, square rootcated like that, like so. Click this on. I'm sorry. What's your problem? What do you mean that's not recognized? Oh, because it's these equals. It's not Excel, Jay. Attaboy. Okay, now if you turn this feller off down here, you'll see that it's, first of all, it's the top half of my graph, number 1. But it's only part of my top half. So this one, for whatever reason, decided to clip it. Thanks, stupid computer. And so I'm going to fix that real quick so it's not clipped anymore. But that's what happened. And then note that because you are you're trying to do an explicit function, that is z equals, you're going to have to do it in 2 pieces, of course, because all you were getting was the top half, if you will. And so there you go. And the nice thing, of course, about having the implicit function, it graphs the entire thing. We'll be doing both of those quite a bit, so just heads up. Heads up, we'll be using that quite a bit in the computer. I just think it's kind of a handy, neat little device to take a look at. Cool. Nice. All right, then. So let's try this one here, for instance. Let's suppose, yes, you wanted to have a sphere with center at 6, 1, 5, nice, and passes through, I don't know, 10, 5, because I feel like it. Cool, nice. So what do you know? Well, you know, if this is one of the points, that's the center point, and this is one of the points up here, what you know is there's a distance from hither to yon, and we're going to call it the radius. So to find that fellow, we need to find the length. So it's going to be 10 minus 6 is 4 squared. Whether you do negative or positive makes no difference. It's the delta x plus the delta y plus the delta z all squared, square rooted. So 5 minus 1 is 4. Well, that's weird. I didn't mean to do that. And then 19 minus 5 is 14. So what is that? 196 plus 32. 228. So the square root of 228 is what it is, friend. I don't know what it is. It is what it is. So what I know is this. I know that my equation of my circle, or my sphere rather, will be x minus, and my center is here. So it's going to be x minus 6 squared plus y minus 1 squared plus 19 minus 5. No, not minus 5, you clown. Sorry. Back that up, Jay. Z minus 5. There you go. Out of bed. Squared equals the square root of 228 squared. Or another way of writing that would just be to say x minus 6 squared plus y minus 1 squared plus z minus 5 is equal to 228. What is this? Well, this is delta z squared. And this is delta y squared. And this is delta x squared. That's all it is. So if you graph this fella right here, you will get a circle that has 6, 1, 5 for a center, and it will pass to the other point in question. So let's do this for fun, shall we? All right. So let's do an implicit surface. And, oh, fiddle faddle. Fiddle faddle, I say, sir. There we go, you big dope. You big goober. All right, so, again, we're just getting comfortable in section 1. No one should go home and I don't want, well, you're already home. Don't cry and say, I don't want to quit tonight. It's not that bad tonight. Wait till tomorrow to quit. Okay, I'm joking. Don't quit. You need to call me and say, Jay, I need help. If you need help. If you don't need help, don't call me, I guess. But I want to help. I care. It's for the children. Now, note that if I'm graphing this sucker, then my x's, first of all, the square root of 228 is like 15 point something. It's a little over 15. So that means that my x is going to be centered at 6, and I'm going to go 15 in either direction from that. That's going to put me at, what, negative 11. I'm going to go negative 12 on this end, and then I'm going to go 6 plus 15 is, 6 plus 16 is 22 on this end, I guess. And in the y-axis, I start at 1. So if I go down 16, it puts me negative 15. And it puts me at 17. And in the z, we started at 5. So if I go 16 in that direction, that's me negative 11. And if I add 16 to 5, I'm going to get 21. Beautiful. And let's see here. Now, oopsie daisy. Now, you'll notice it graphs it. Be like, I can't see it, Jay. I know. I am working on it, pal. Negative 12. And 22. And negative 15. And 17. Fair warning that when you do this, until you hit enter, nothing happens. So I'm just arrowing and clicking around, so nothing's happening yet. If you hit enter every time, it would update it. Now note that we need to get up to, on the z-axis, you need to get up as high as 21 and down low as like -11. So I'm going to change those. If you don't, it'll just cut it off, and that's kind of annoying. And then another thing that's kind of nice is if you change your focus point, and you don't have to, but if you change your focus point to 6, 1, 5, as where our center was, then the graph, that'll kind of put that in the middle in theory. What's going on here? Ah! Okay, something was went weird here. Why am I only seeing part of it? Okay, I'm going to pause you for a minute while I figure out what I did wrong. Something a little screwy here. Well, the main thing I didn't do is I didn't hit enter up here. So come back up here, hit enter, and that will change your window. For some reason, it didn't update, so whatever. There it is. Cool. Nice. And what a guy can do, then you come in here and you go, let's add a point. Can we put a point on there, Jay? I'd love to. What point do you want to put on there, Jay? I think I want to put on 10, 5, 19. That's what I want to put on there. So 10, 5, 19. And I like to make my points a little more garish, so they stand out like a sore thumb, so I can find them. I don't like to have to go searching around for my points. If I do that, when I scroll around, oh, there it is right there. Look at that. Where is it, friend? By God, look at it. It's right on the surface. Shut up. No, for real. For real. And there it is. Bam. Bam. Bob's your uncle. Piece of cake. Okay? We love that. We love it a lot. Okay? So, again, that's how the game would be played when you're doing this guy. Okay? It's pretty straightforward. I'm going to demonstrate one here that I'll never make you do. Well, that's not true. But I don't think I'll make you do it for the test. How about that? But I do want you to see this because I think it's kind of a big deal, algebra-wise and visualization-wise. So if I have 3x squared, yes, 3x squared plus 3y squared plus 3z squared plus 6x plus, no, let's do minus, that's hot, minus 9y, because I'm a nice guy. Plus 10. No, plus 10. Should I do plus 10? I do minus 10. That I know it'll work. Minus 10 equals 0. Hey, can you put this into standard form of a sphere, Jay? Well, I'd love to. So standard form of a sphere would be something like this. X minus a squared plus y minus b squared plus z minus c square equals r squared. And that's what I like to do. But to do that, I'm going to do some fancy factoring. Okay, and so to pull that off, here's the game. First of all, do I know it's going to be a sphere? I do. These guys, the x, the y squared, and the z squared, all have the same coefficient of 3 out front. So therefore, I know beyond a shadow of a doubt when I'm done, I will have a sphere. If one of them was a different one, then I would be like, I might have an ellipse, ellipsoid, I could have some cones. I could have a variety of things, but it would not be a sphere if they did not have the exact same coefficients. So what I'm going to do is I'm going to group these guys together. I'm going to leave a little room to work. Put all my y's and my x's together, then my z's. Give yourself a little room, stupid. Plus 3z squared. And then I'm going to say equals 10 because I want it on the other side. So what you got to do here is complete the square. But before you do that, let's factor that 3 out because that makes it kind of nice. Hey, so what do you have to put here so this thing factors as something plus x plus something squared? What do you have to do? Well, that's called completing the square. And so if you do that, what are you going to do? Well, what you're going to do is you're going to take half of 2, which is 1, and square it. So you're going to get 1 squared, which is 1. Notice that the 1 is inside of inside the parentheses, and so everything in the parentheses gets times by 3. So in reality, you've added 3. Well, if you're going to add 3 to this side, you better add 3 to the other side. Nice. Same deal here, more or less. Cool. And so what's half of 3? What's half of negative 3? Well, it's negative 1.5 squared. That's what it is. You with me? It's always divide by 2 and square that dude. All right, so you're like, oh, what's 1.5 squared, Jay? I don't know. Let's find out. That's not true. I know what it is. It's 2 1/4. There it is. All right, but notice it's inside the parentheses, so times 3. So that's 6.75. So I better add that to the other side as well. All you're doing is changing the way these things are dressed up. That's it. So this piece here will factor x plus 1 squared. This one will factor y minus 1.5 squared. 19 3/4. Cool. I don't want those 3s, so I'm going to divide everybody by 3, and I'm going to get x plus 1, y minus 1.5, z squared equals, I don't know, what is that? 6 and 3. 6 and something. Wait, where's my calculator? 19.75 is 6.5833. 6.5833. Sweet. Boom. Boom. There you go. And that's it, friend. That's kind of ugly. I wouldn't probably do that one. So ugly to you on the test. A little complete in the square, though. A little complete in the square. Could you have divided by 3 right off the bat and done it that way? You sure could have. You sure could have. That would have been fine. Tell me this. Where is this circle centered? It's centered at -1, 1.5, and 0. Because it should be x minus a. But this is minus a minus 1, so -1. This guy here is y minus b, so boom, there's b, and then this of course is just minus 0, so 0. That's where it is. And the radius is the square root of 6.5833, whatever that boils down to, 2.5 or something. No, 2.7 or something. 2.6, whatever it is. I don't know. Don't care. Okay, if I cared, I'd do it. All right, here's another one, just for fun. What are you doing? Let's don't do that. X squared plus 4x plus y squared minus 30y, there you go, babe, plus z squared minus, why do you keep trying to write a freaking 3, stupid? Why do you do that? What is wrong with you? The other day, this girl in my class in high school said, Mr. Grimm, you shouldn't, how did she put it? You shouldn't bully yourself. I said, leave me alone. Anyway, check it out. So x squared plus 4x. All right, what's half of 4? Well, it's 2. So I'm going to take 2, and I'm going to square it. Nice. What have I really done? Well, I've added 4. And if I add 4 to this side, I'm going to add the 2 over here already. So I'm going to have the 2, plus I'm going to add 4 more to this side. Nice. And then I'm going to do y squared minus 30y. What's half of negative 30? It's y, it's negative 15. And what is negative 15 squared? Well, it's 225. And then z squared plus 6z, and then half of 6 is 3. 3 squared is 9. Add 9 to both sides. And boom, we're done. X plus 2 squared, y minus 15 squared, z plus 3 squared. Good criminy. It's 15, 240. Boom. So the radius, I'll do the hard part, is the square root of 240. And the center is going to be at negative 2, 15, negative 3. Bam. Done. Nice. Okay. That's the kind of thing that you're going to see a lot of in this section, section 1. There's a couple other things I want to just mention. If a guy were to graph this in 2 dimensions, what would you see? In 2 dimensions, you'd see a vertical line. It would look like so. You're like, that's cool. What would that look like in 3 dimensions? Okay, this is in R2, we say. In R2, it's a line. It's a vertical line. But in R3, what would it look like? This is why I want you using this sort of graphing program. When I was a kid, we didn't have access to this sort of thing, and we had to just kind of like memorize stuff. And you're like, well, I hope that's right. And you're like, no, it's clearly obvious. And you're like, no, sure is not. If you look down here, it says function. It says x equals. It's one of the lesser known ones. I mean, it's one of the lesser used ones. So it's towards the bottom. It's still there, but it's not as used as has it been the z equals one. So you just go x equals 2. Boom. Hit enter. Hot dang, what do you know? It's a plane. What? Like literally it's a plane, man. It is. It's a plane. So x equals 2 in R3 we say is a plane. Nice, that's great. Well, that's interesting. Well, let's do another one, shall we? Let's do x squared plus y squared equals 9. You're like, OMG, gosh, in R2, that would be a circle. You're like, all right. So in R3, it would be a sphere. Wrong. Like, what do you mean wrong, Jay? Yes, no. In R3, check it out. In R3, it is not a sphere. Because guess why? There's no z on here. In other words, z is not constrained. What do you mean? What do you mean it's not constrained? It means z is not pinned down. The biggest that y could ever be is 3. And I know that because 3 squared is 9. That would force x, though, to be 0. But in this case, z is uncontained. In fact, z can be anything. And so, if you come over here and look at this, this is the whole point of why I want you to graph it on these guys, is so that you can see kind of how these pieces all fit together. And you can kind of go, oh, right on. So implicit surface, you just go, boom. Well, x squared plus y squared equals, what did I say, 9? I think I said 9. Oh, of course it's not going to show up because, of course, this freaking thing is not grabbing correctly. Why did I just say 4? It would have been so much easier. Think about your life choices, Jay. Why couldn't you have done things right, you idiot? I don't know. Mr. Groom, I mean, I feel like you shouldn't berate yourself so much, Mr. Groom. Why not? I'm a loser. Boom! OMG, Hosh! What do you know about that, friends? It's a cylinder. What? Yes, yes. This would be a cylinder in 3 dimensions. Okay, now again, pay attention to what that means. If it was x squared plus y squared plus z squared equals 9, then it'd be a sphere. But the fact that we don't have a z here says that z can be whatever it wants to be. Kaboom! Kaboom! And by the way, going back to this problem over here, I forgot to mention something here. X equals 2. Okay? So, for instance, the point 2, 9 in 2 dimensions would be on that graph. So would 2, 6 and 2, -1. All I know is that the x has to be 2. But in 3 dimensions, 2, 1, 5 would be on the graph. 2, -2, 6 would also be on the graph, and so on, so forth, and so on, because x is equal to 2. Literally, that's what it is saying. I love saying literally that way. Quite makes me happy. How would that change if you did y squared plus z squared equals 6? Well, let's don't do 16. It's too easy. Equals just do 9. You're like, gosh, I feel like it'd be the same picture, only not. I feel like it'd be like different. I feel like it would be, I don't know, like weird. Weirdly the same, but oddly different. Yeah, there you go. Oh, sweet. Nice. That's hot. Enter. Oh, looky there. It's a sphere, you see. But look, down. We're looking down the y-x barrel of the thing, yes? We're looking down the x-axis. And just like on the last one, we're looking down the z-axis. Because this time, x is not mentioned. Therefore, x can be whatever it wants to be. But the z and the y are constrained because z plus y, z squared plus y squared has to be 9. And no bigger. Thank you very much. Thank you very much. Now, obviously, you can do things like this. For instance, what if I made this a less than sign? Maybe I can do that without using my keyboard. Maybe. Nope, sure cannot. Let's get the old keyboard back on there, G8. You goober. A little less than action. Oh, boom. There's an error in your implicit function. Oh, probably. Well, it's not helpful that that's capital, but I don't think it's going to graph it. Sorry. There is no way to do that on this one. I'm sorry. But listen, that's okay. I forgot you can't do that on this one. So anyway, if I did less than, it would just fill in that thing. It would be just a hollow. It would be, instead of being a hollow cylinder down the axis, it would be the solid one. It would be everything inside of it. And you couldn't graph it, but you could definitely describe what it would look like. Pretty straightforwardly. Okay. What if you did, hypothetically here, what if you did, what would, I don't know, let's see, y squared equals 4 look like? Like I don't know, Jay. I don't know either. Let's find out. So again, that is going to be an implicit function, or an implicit surface, rather. You simply come in here and go, I don't know. Now, if it was y squared equal 4, it's two planes. Well, that doesn't shock me terribly. What if I did equals 4 minus x? And you're like, I don't know. I think you do. I think you do. I think you realize that you could do x is equal to 4 minus y squared. And I feel like that's going to be a parabola. Oh, it's a little cut off here. Let's make that a 3. How about? So I don't have to do any more work. Boom. It's a parabola that just goes and goes and goes. It goes down the z-axis like this because z is not mentioned. Does that make sense? Z is not mentioned at all. And so it, in essence, becomes a parabola. And so the idea here is you're going to be looking at some fairly normal-looking ones, like, oh, I know, y equals x squared. Well, if you're going to do y equals, you typically do it this way. You know, an implicit function, you do this. If it was y equals function, you just go y equals, I don't know, let's say x squared minus 9. Oh, not minus 8. That's stupid. Minus 2 or something. I don't know. Boom. Why does it say? Oh, because I did x squared, x to the minus 2. That's cute. I won't do that to you tomorrow. We will do those later on. There we go. No, nice. Look at that. It's a parabola, just like we thought it should be. Okay? And a lot of the same stuff that we've been doing over the years is going to come to fruition in this class. You're like, oh, dude, check it out. And you're like, what? Look at that. These guys have positive slopes on this side. They do. And they have negative slopes over here. That's right. Well, will it change wherever we go? Sure it will. Sure. And then if you get all jiggity with it here, what? Oh, let's make it cute. Z to the third. Oh my goodness, look at that. Everything's all weird and strange and goofy and OMG, gosh, it's a mold of something, I feel like. It is. And these traces, you can see these lines on there. You can see they're tracing things out. It looks like a cubic function. It does. That's because the z is a cubic function. And from the side over here, geez, it looks just like a parabola. That's because it's x squared, and x squared is a parabola. That's right. And if I swing around this side, geez, it looks like that goofy. Well, if I can turn it just the right way, it looks like a cubic function again. It should, because it's a cubic function, in essence. And so when you look at these guys, we're going to be talking about this a ton later on. So I want chapter 9, section 9.1 is getting comfortable with doing a little bit of algebra, not much, and also looking at what some of these graphs look like and just getting comfortable with things. The rest of it I'm just going to leave for you to look at. There's nothing that's too terribly different there. It just really isn't that tough. And then the next section will be 9.2. And in 9.2, we are going to be discussing vectors, starting our discussion of vectors, one of my favorite topics.